Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a video in a series of videos on inverse trigonometric functions that is for both a trig course and a pre-calculus course. So if you are in pre-calculus or trig, you should be fine watching this video for inverse trigonometric functions and evaluating compositions of them. Prior to watching this video, you should be familiar with inverse trig functions, how to evaluate them by themselves, and then also you should know the definitions of inverse trig functions. If you don't know those, I have videos in the series for that. The way we're going to tackle them in this video here is we're going to look at four cases. These four cases are that you're given a trig function, like let's just pretend it's the cosine, and we're going to evaluate it at that very same trig function inverse. So cosine of cosine inverse of a ratio. Now remember, inverse trig functions always have ratios as their arguments. Their outputs are angles. The second case will be very similar. However, it'll be where we evaluate a trig function at a different inverse trig function. So for example, like a cosine of a sine inverse, again, of a ratio. So that'll be our second case. And then the next case, we'll switch the direction of the composition and we'll look at the inverse trig function evaluated at a trig function. That is a cosine inverse evaluated at the cosine of an angle. Remember, trig functions take as their arguments angles, they output ratios. And then finally, we'll take two different trig functions. We'll evaluate the inverse trig function of a completely different trig function. For example, a cosine inverse of a sine of an angle. These comprise the four cases when you're evaluating compositions of trigonometric functions and their inverses. The easiest of these cases is the very first one that we have in front of us. Now, I want to repeat something I've mentioned in a previous set of videos, actually quite a few videos, is that really when you're dealing with trig functions, it boils down to two things: reference angles and quadrants. However, sometimes with compositions, you don't need both of those pieces of information. Generally, just quadrants will be fine. But with the cosine, or not cosine, I should say, but with these first two cases here, where it's trig functions evaluated at inverse trigonometric functions, so case, let's just say 1 and 2 here, you don't even need quadrants. You pretty much have everything you need given in the problem. So let's go ahead and see how this would work. To master this material, you just have to remember a couple key pieces of information. First thing, the inverse trigonometric functions return angles. So this is actually asking you, what is the cosine of an angle? That's the very first thing you need to remember, that this inverse trig function is just an angle. The second thing you need to remember is that you should probably tell the world what that angle is. So I'm going to say where theta is equal to the cosine inverse of 3/5. Now you should not grab a calculator, because this tells us don't grab a calculator. And you might say, but that's not a special ratio, so I don't know what the special angle is for this. And I would tell you, you don't need it, actually. You really don't. Because this implies, by definition of the inverse trig functions, that cosine of theta will equal 3/5. Now, technically, we are done with this problem because we have just started with cosine of a cosine inverse of 3/5, where we've said, well, that's the same thing as cosine of an angle. And that angle satisfies that the cosine inverse, it's equal to the cosine inverse of 3/5, which implies whenever I see the handwriting cosine of theta, I can replace it with 3/5. Sounds very circular. I totally agree. This is a rare case where you have a trig function, cosine, evaluated at its own inverse, cosine inverse, and they cancel each other out. And it just becomes that 3/5. It's because they are inverses of each other, and the cosine is unrestricted. Now, I do want to continue this forward, even though we are technically done with this problem, because I want to showcase what you would do in general if this wasn't a cosine of a cosine inverse, but instead a cosine of a sine inverse or something like that. I would first look at, well, okay, I've arrived at cosine of theta is equal to 3/5, because again, theta was cosine inverse of 3/5. Well, cosine is positive in quadrants 1 and 4. However, our angle here is either quadrant 1 or 2, because that's where the cosine inverse is going to return. So I know whatever angle this is, it's going to be an angle between 0 and pi. I'll even write that down. The angles between 0 and pi. It actually can include those edges as well. However, we have a positive ratio, 3/5. So cosine is positive. So I'm going to say this implies theta is an element of, or the angle terminates in, quadrant 1. Of these two possibilities, quadrant 1 is the only quadrant where we're going to have a positive ratio. So we know our angle must be in quadrant 1. And now all I'm going to do is draw a triangle with that angle theta in quadrant 1. It's a right triangle, by the way. The adjacent side to that angle is 3. The hypotenuse is 5. If we needed it, I could find that missing altitude, but we don't need it because the question really was asking, what is the cosine of theta? Well, the cosine of that theta is 3/5. But this entire setup is how you'll tackle all of the problems that are of the forms 1 and 2 here. They all are done the same way. So let's see how that's done in a future problem. Here we're given the cosine of the tangent inverse of 3/4. So this is that second case where we have a trig function evaluated at the inverse of a completely different trig function. How do you deal with this? Well, again, I start with the fact that this is just the cosine of some angle. And then I state to the world, oh, by the way, if you're curious, that angle is equal to the tangent inverse of 3/4. Which implies, by the way, by the true definition of an inverse function, that the tangent of that angle must equal 3/4. Well, there are a couple things I need to take in consideration. The angles that the tan inverse is going to return are between negative pi/2 and positive pi/2. So I'm going to write that down. That theta is between negative pi/2 and positive pi/2. Or in other words, we have angles in quadrants 1 and 4. Of those two possibilities, notice our tangent is positive. So of those two possibilities, which of those two quadrants will tangent be positive in? Well, if you said quadrant 1, you're absolutely correct because all trig functions are positive in quadrant 1. So because this ratio is positive, I know that I'm going to draw a triangle in quadrant 1. Here I go. Here's a quadrant 1 triangle. It's a right triangle, by the way. We are told the tangent of that angle is opposite, 3, over adjacent, 4. And if you use the Pythagorean theorem, you'll find that this hypotenuse is 5. Remember what our original question was? What's the cosine of that angle? You are staring at it. Adjacent over hypotenuse, 4 over 5. Very nice problem to do. Not terribly confusing, hopefully. And we don't have to actually worry about reference angles here. All we have to actually worry about in these problems is what quadrant we're dealing with when we finally rewrite our function as tangent of theta equals 3/4. What quadrant is the tangent positive in? And note, the tangent normally is positive in quadrants 1 and 3. However, because the angle was born of the tangent inverse, it's restricted. That's why we only worry about quadrant 1. Let's try another example. You can tell that I'm really trying to drive this point home because I have multiple similar examples. Usually I don't do this, but this is such an important idea that I want to drive the point home. And in fact, I re-recorded this video just to include more examples. So this is going to equal the tangent of some angle. And somebody says, but what's the angle? I would say, well, the angle is, so where theta is equal to the cosine inverse of 2/9. And that implies that the cosine of theta is 2/9. Now, I happen to know the cosine inverse, it returns an angle, and that angle must be between 0 and pi radians. That is, it has to be an angle terminating in quadrants 1 or 2. Of those two quadrants, the cosine is positive in quadrant 1. Notice there's a theme here. All our ratios are positive. That is because most textbooks only deal with positive ratios when they do compositions. It's not necessary, actually. They should be able to do negative ratios, but I have yet to find a textbook that really concentrates on them. So you'll often see the positive ratios. So we know we have a quadrant 1 triangle. So I'll just draw a triangle here in quadrant 1. And our angle is theta, and our adjacent side is 2, our hypotenuse is 9, and then using the Pythagorean theorem here for this right triangle, we have 81 minus 4, which is 77. So this is a square root of 77. That's the length of that altitude there. And now let's see what the original question was. Oh, what's the tangent of that angle? That's opposite over adjacent, root 77 over 2. So I'll just write that in there, root 77 over 2. I'll zoom back out and just double check my mathematics there. 9 squared is 81 minus 4 is 77. Yes, that works out. Now, I did say that this video is both for trigonometry students and pre-calculus students. The reason why I said that is because in pre-calculus you review trig quite a bit, and honestly in a pre-calculus class, because it's assumed that you've had a full semester of trigonometry, most of the review for trig is very short, with the exception of a handful of sections, and this is one of those sections. Inverse trig functions are so important in pre-calculus and then in calculus, really, that you have to have a solid foundation. So I tend to do full lectures for inverse trigonometric functions in my pre-calculus course, so my trig students and my pre-calculus students share the same lectures. And the significant difference between those two are the use, or I should say is the use, of the arcsecant, the arccosecant, and the arccotangent. In pre-calculus you use those. In trig, you don't really see the arcsecant that much, or the arccosecant, or the arccotangent. So in this case, this is very much dedicated to my pre-calculus students, but I think it's very important for a trig student to watch this as well. It's not actually that much more difficult, in fact, not at all, versus the previous example. So Again, remember the arc notation just means inverse. So this is the same thing as saying the sine of the inverse secant of 17 over 11. Let me finish that out. And all the inverse trig functions, including the secant here, they all return angles. So this is just going to be the sine of an angle. And we do have to state what that angle is. So I'll just say where that angle is equal to the secant inverse of 17 over 11. Well, what does that imply? That implies that the secant of that angle must equal the ratio 17 over 11. But here's the critical piece. Theta, I think I was using blue ink before, so I'll continue with that. Theta, it is restricted to be an angle in two different quadrants, just like we have all inverse trig functions return in two different quadrants. For example, the cosine inverse returns in quadrants 1 and 2. The sine inverse returns in quadrants 1 and 4. The secant inverse is a weirdo. It returns in quadrants 1 and 3. So theta is between 0 and pi over 2, or, I shouldn't say and, I should say or. It is between 3 pi, or pi, and 3 pi over 2. It is a weird function like that, the inverse trig function, the inverse secant function. But just note that's quadrants 1 and 3. Of those two quadrants, where is the secant positive? Because that's what we're dealing with, a positive ratio here. Well, quadrant 1. So again, you start thinking, well, do I even have to worry about the negative quadrants? Yes, you do. For right now, we're just dealing with the positive ratios, but I have a rare case where you do deal with a negative ratio coming up. So anyhow, I happen to know that my triangle I'm going to draw is in quadrant 1. So let's go ahead and draw a quadrant 1 triangle, just like we did in the previous problems. So this is really no different. So it doesn't really merit any major concern as far as, oh my gosh, this is pre-calculus level, this should be harder. No, it's not really harder. It's just a completely weird function, the secant inverse, but that's about it. Remember, secant is hypotenuse over adjacent, so 17 over 11. And that will mean that this length is square root of 168. Technically, that could be reduced. By the way, it's not that I knew that offhand. I actually had to grab a calculator to figure out the 17 squared minus 11 squared. I mean, I could have done it by hand, but I just didn't bother. So if you're thinking like, oh my gosh, do I have to memorize these? No, you have to do just mathematics here. So square root of 168, but that is technically divisible by 4. And 4 goes into 168 42 times. Let's see, does 2 and 21. Yeah, okay. So this will be 2 root 42. All right, not that big of a deal. I just wanted to reduce that down a little bit. Good old, if you've learned it before, then you're going to use it. So we've learned to reduce radicals, so we're using that. Anyhow, but what was our original question? Oh, what's the sine of that angle? What's opposite over hypotenuse? Well, opposite is 2 root 42, hypotenuse is 17. So the answer here is going to be 2 square root of 42 over 17. And that is the full worked out problem for something that would normally be reserved for pre-calculus, but you could see you could easily do this in a trig course. Now here comes the negative ratio example. So we have the secant of the cosine inverse of a negative 1 over 5. Well, that's just a secant of an angle. Let me write that in there. Secant of an angle where the angle is equal to the cosine inverse of a negative 1/5. And that implies that the cosine of the angle is equal to a negative 1 over 5. Remember, cosine inverse returns angles between 0 and pi, or in other words, in quadrants 1 or 2. Now you're seeing a ratio that is negative. So we have a quadrant 2 angle. That is the difference here. That's the only difference. So when you have a negative ratio, just consider where your inverse trig function is going to return and which of those two quadrants would your trig function be negative in. So let's go ahead and draw a triangle in quadrant 2 rather than quadrant 1. That's the only difference. Kind of nice, actually. So here's our triangle opening up into quadrant 2. I would be lying to you if I said this was theta. That's actually not theta. Truthfully, theta is this angle right here. This black angle is theta hat, which is an important angle. It's our reference angle. But I'm still going to treat it like it's theta, but let's just go ahead and worry about adjacent and hypotenuse here because that's what we're dealing with. The adjacent side will be a -1 because x values are negative in quadrant 2, and the hypotenuse is 5. So the reason why I had to make a big statement about the x value being a -1 is because the hypotenuse will never be negative in any of your triangles. The hypotenuse is always positive. So if you're trying to figure out where that negative here is going, it's going to be attached to not the hypotenuse. That's a great way of saying it. It's just not attached to the hypotenuse. Anyhow, let's go ahead and figure out via the Pythagorean Theorem what that length is if we need it, which we technically don't, but let's just pretend as though we do. So that would be square root of 25 minus 1, or square root of 24, which is 2 root 6. And it's positive because it's in quadrant 2 and it's the y value. So it's up 2 root 6 units. And now I will go back to the original problem. What did I want? I wanted the secant. The secant is hypotenuse over adjacent, the hypotenuse being 5, the adjacent being -1, and so this would be a -5. Now, I find that that problem is not enough to really drive home the point of those negative ratios. So trig functions of inverse trig functions of negative ratios. So if I don't have another one next, I'll come back here and I'll make up a problem. And I just checked and I don't have another one next, so I'm going to make up a problem. So let's make up a problem like this. Let's suppose that we're dealing with, let's make it kind of interesting. Let's do the, we already did a secant inverse. Let's do a tangent of a cosecant inverse of a -7/5. I think that's a pretty good problem. So let's suppose that we're being asked to evaluate that. This is a pre-cal level problem. And so this is equal to the tangent of an angle. I feel pretty confident about that, where the angle is the cosecant inverse of a -7/5. But that implies that the cosecant of that angle is a -7/5. Now let's talk about where that angle could return. Cosecant inverse and secant inverse are both oddball functions. They're just weirdo functions. And they both return angles into the same quadrants. Specifically, they return angles between 0 and pi/2, or pi and 3pi/2. Sorry, I was having a brain fart there. So now you might have noticed in the secant inverse example, the inclusion was here on the 0. And in the cosecant inverse, the inclusion's on the pi/2. To be honest with you, you're not really going to have very many cases where you have to worry about those included edges. So the main thing to note is that it's either quadrants 1 or 3. That's the main thing to note here. So don't really freak out about the, oh my gosh, do I have to memorize if it's included at 3 pi over 2 and pi over 2 here? No, don't worry too much about that. What you should worry about is what quadrants the secant inverse and cosecant inverse return their angles into. And in this case, it's quadrants 1 and 3. In both cases, in fact, cosecant inverse and secant inverse. Of those two quadrants, where is the cosecant going to be negative? Well, it's definitely not quadrant 1 because everything is positive in quadrant 1. So it must be quadrant 3. So here I'm going to draw a quadrant 3 triangle. Here I go. I'm just drawing out a quadrant 3 triangle here. A little right angle. And we're told that the cosecant, which is hypotenuse over opposite, is negative 7 over 5. Negative 7 over 5. Which one gets the negative? Well, remember, hypotenuse, they are never going to be negative. They're always positive numbers. So the negative is going to be on the 5, and that should make sense. You went down 5 units in the y direction. By the way, this is a terrible looking right triangle. Sorry about that. So now we're going to go ahead and use Pythagorean Theorem to help us find that missing side length right there. 49 minus 25 is 24. And so this will be the negative square root of 24. I say negative because if you look at that x value, it's going back along the x-axis. So it has to be a negative number. So it's going to be a negative square root of 24, which is negative 2 square root of 6. And remember, technically speaking, this blue angle is actually what theta is, but we can go ahead and pretend as though this angle right here is actually theta. It's totally okay. There's nothing wrong with that. Okay, so let's go ahead and do this. The real question was, what's the tangent of theta? Well, tangent is opposite over adjacent, so it'll be a negative 5 over a negative 2 root 6, or in other words, 5 over 2 root 6. 5 over 2 root 6. By the way, this is one of those cases where I tell my students don't bother rationalizing denominators. It's an antiquated technique. However, this is one of those cases where you might want to. If you wanted to, you could. You don't have to, though. I'd probably leave it like this. All right, so that is a good example of when the ratio is negative and you have a weird function like a cosecant inverse or a secant inverse. Not very common, but it does happen. Now we're going to go into cases 3 and 4. Cases 3 and 4 occur when you're taking the inverse trig function of a trig function. And these are a little bit more complicated. That's why I saved them for the back half of this video lecture. Rather than teaching you a whole new method, I'm going to actually just reinforce a method here. This may look different, but it actually is not too different than what we've previously been doing. It is critically important, again, that you remember inverse trig functions return angles. This is an inverse trig function, so it is going to return some angle. Now we'll just go ahead and say where the sine of that angle should equal the argument inside, the sine of 330 degrees. Now, a lot of students at this point will make the terrible mistake of saying, oh, therefore theta is 330 degrees. But that is not true, because theta, which is the angle returned by the inverse trig function, is restricted. So I'll use the same blue ink I've been using all along, and I'll say, well, that theta has to be between negative, since we're in degrees, I'm going to say negative 90 degrees and 90 degrees. The sine inverse cannot return a 330 degree angle. It just can't do that. So what are we going to do? Well, oh, by the way, I should probably say, maybe I should say that. Quadrants 1 and quadrants 4 is what the angle will return into. So how are we going to handle this? Well, the easiest way to do this is this is where we're going to have to concentrate on reference angles and quadrants. So we're going to have to focus on a quadrant and then focus on a reference angle. Well, let's take a look at this. I know that whatever angle gets returned, the sine of that angle should equal the sine of 330 degrees. Let's start by asking what is the SIGN sign, plus or minus sign, of this angle. Well, if we really take a look at this angle right here, that's a quadrant 4 angle. No, this does not mean our answer is going to be in quadrant 4. It just means that the sign will be negative because, again, 330 degrees is in quadrant 4. So this is equal to some negative number. That's all I really care about. I just care, is the sign going to be positive or negative? Because once I figure out if it's positive or negative, I can then say, oh, of these two quadrants that this sine inverse is going to return into, it's got to be the quadrant where the sign is negative. So I have a quadrant. Now I need a reference angle. Well, what is the reference angle for 330 degrees? Again, I'll just point at this and I'll say the reference angle here is 30 degrees. So again, remember, trig functions of an angle are almost the same as their trig functions of their reference angles. They might be off by a plus or minus sign. So sine of 330 degrees is very close to sine of 30 degrees. We just have to worry about the plus or the minus sign. And that occurs, or that gets fixed, when we note that our angle is going to terminate in quadrant 4. So we have a reference angle, I'll highlight that, and a quadrant. Now I know our answer will be an angle between negative 90 degrees and positive 90 degrees. That angle will be in quadrant 4, and it will have a reference angle of 30 degrees. Again, it'll be an angle in quadrant 4, and it'll have a reference angle of 30 degrees, so the actual angle will be a negative 30 degrees. So thus, the sine inverse of the sine of 330 degrees is going to be a negative 30 degrees. There you go. That's how that problem is done. And this is such a hard topic for students that one example is not going to do. So let's do some more. The cosine inverse of the cosine of, who cares? It's not that big of a deal. It's the cosine inverse. Cosine inverse is going to return an angle. Okay. Where the cosine of that angle is going to equal the argument right here, which is the cosine of 7 pi over 4. Again, this does not mean that theta is equal to 7 pi over 4, because the cosine inverse only returns angles between 0 and pi. Notice how we constantly have to remember where our inverse trig functions return angles. These are quadrants 1 and quadrants 2. Now we'll go ahead and just take a look at this cosine of 7 pi over 4. Notice 7 pi over 4, because just to bring it back to what I talked about last time, we need to figure out what is the plus or minus sign of this cosine of theta. Well, this angle right here is a quadrant 4 angle. And in quadrant 4, the cosine is positive. So this is equal to some positive number. I don't really care what the number is, honestly, even though we can easily evaluate that to be a 1 over root 2. I don't care about that. That's not actually what I care about. I just want to know, is it positive or negative? Because if it's positive, then I know the cosine inverse is going to return either between quadrants 1 or 2, it's going to return in quadrant 1. Because again, we know the cosine is going to be positive. So we have an angle, and we're taking a cosine inverse of something to get to that angle. That something, the cosine of 7 pi over 4, is positive. So we're taking the cosine inverse of a positive number. That means our angle should be quadrant 1. Now all I need is a reference angle. The quadrant's done. All I need is a reference angle. Well, look at this angle, 7 pi over 4. What is the reference angle to 7 pi over 4? At this point, you should be pretty legitimately an expert at finding reference angles. This reference angle is going to be pi over 4. So a reference angle of pi over 4 in quadrant 1 means that our actual angle is pi over 4. Again, you open an angle in quadrant 1 that has a reference angle of pi over 4 means the actual angle is a pi over 4 as well. And so therefore the answer is pi over 4. Notice it did not return 7 pi over 4 because the cosine inverse cannot return an angle that large. All right, let's try another one. The arctangent of the tangent of 31 pi over 6. Now that angle, 31 pi over 6, is so large, I know there's no way the arctangent will ever return an angle that large. But it does, the arctangent does return an angle where that angle satisfies the following. The tangent of that angle must be the interior function tangent of 31 pi over 6. Again, that does not mean your angle is 31 pi over 6 because that angle is way too large. So what is our restriction for our angles if we're dealing with the tan inverse? Well, the tangent inverse only returns angles between negative pi over 2 and pi over 2. How do I know we're dealing with radians? Because that's what they handed me there. All right, so let's go ahead and, I don't know why my eraser's not working. I'll just do it this way. All right, let's go ahead and state the quadrants. That'll be quadrant 4 and 1. And now we have to figure out, what quadrant does 31 pi over 6 land in? Well, remember, you can kind of rewind the tape a little bit. 31 pi over 6, or tangent of 31 pi over 6, is the same thing as tangent of 31 pi over 6 minus 2 pi. So I could start rewinding by sizes, step sizes of 2 pi. 2 pi is the same thing as 12 pi over 6. So if I rewound by 2 sets of 12 pi over 6, I'd be rewinding by 24 pi over 6. And so this should be the same as the tangent of, let's see, 31 minus 24 is 7 pi over 6. Let me just make sure. 31 minus 20, yep, 7 pi over 6. Okay, so all I did was rewind the tape a little bit and getting it down to 7 pi over 6. Technically, tangent is pi periodic, so you could actually subtract a pi off that. But I think that is not going to be instructive for this example. So let's just continue forward here just as written. So I have a quadrant 3. Oops, let me use blue to keep everything the same. That's a quadrant 3 angle, right? And tangent in quadrant 3 is positive. So I know that whatever angle, actually, maybe I should say it this way. I know that I'm looking at the arctangent of a positive number, and that should equal some angle. So what quadrant is arctangent positive, or what quadrant would arctangent return in so that the tangent is positive? Well, that'd be quadrant 1. So I know my angle is in quadrant 1. Whatever my answer is, it's going to be a quadrant 1 answer. And now I just need the reference angle, and that is also somewhat obvious because our reference angle, just from our experience with reference angles, is pi over 6. If you need to review that, I have videos on that. There are several, maybe like 15 to 20 videos ago, but you should be able to find my reference angle video. But we know the reference angle is pi over 6. We're in quadrant 1, so reference angle quadrant done. So that means our actual angle is pi over 6. Not bad. Okay, so we've kind of covered all the bases for the, I don't want to say easy, because I actually am teaching this in the same way that, in such a way that you would tackle the harder problems relatively simply the same way. So let's go ahead and move on to those quote unquote harder problems. Oh, I didn't realize I had something like this coming up next, so we might as well just tackle this guy right here. The cotangent inverse of the cotangent of negative 31 pi over 2. I thought that I was moving on to a different example, but I guess I'm not. So this should be an angle. I say should be because there might be an issue with this. And that is where the cotangent of that angle should equal the cotangent of a negative 31 pi over 2. Now, remember what we did last time. I just started rotating by 2 pi. So 2 pi is the same thing as 4 pi over 2. So I'm going to add a bunch of 4 pi over 2s to this so I can rotate it to an angle that's easier to deal with. Maybe 8 sets of 4 pi over 2. If you add 8 sets of 2 pi or 8 sets of 4 pi over 2, this will be the cotangent of pi over 2. And the cotangent of pi over 2, that's actually a quadrantal angle, or what I call an axial angle, but it's quadrantal angle, honestly. And the cotangent of pi over 2 is actually 0. But let's pretend as though you didn't remember that. You should remember that, but let's pretend as though you didn't remember that. Now, remember this. The angle that gets returned by the cotangent inverse. Now, this is for pre-calculus students, but it's still important enough that I think trig students should watch this as well. The angle returned by an inverse cotangent is going to be an angle between, oops, I was going to write pi there, between 0 and pi. So, is that angle already between 0 and pi? If it is, it's just returning that angle. And that's actually the rule of thumb for all of these. If whatever angle you have here is within the range of what your inverse trig function would return, you're literally just going to write that down as the answer. So in this case, pi over 2 is within the range of 0 to pi, so therefore that is my answer. It's just pi over 2. All right, the perfect. That's a nice problem, not terrible. Now we get to the fun ones. And these ones I actually do find to be kind of interesting problems. Not because they're hard. They're actually not hard at all, but they're just interesting problems to me. All right, cosine inverse of sine of pi over 6. Now, that is obviously a special angle, right? You totally get it. It is a special angle. So if I were to do this using the methods that we had created thus far, we'd say, oh, this is a cosine of theta, or cosine inverse is equal to some angle, where the cosine of that angle must equal sine of pi over 6. Well, this is kind of an interesting problem. Because these are not the same trig functions, it's a cosine inverse of the sine, you can't just say, oh, well, that sine is going to be positive, therefore and let me find the reference angle and all that fun stuff. It's not going to work well like that. So the only way you can really tackle a problem like this is if they hand you an angle that you're already familiar with. In other words, a special angle. So if somebody handed this to me, honestly, I would just say, okay, I know what sine of pi over 6 is. So I would just write it this way. This is the cosine inverse of sine of pi over 6 is 1/2. And then I would look at my special triangles. Remember, this is an angle. That's what cosine inverse is going to return. So it returns an angle such that the cosine of the angle is 1/2. We know that the angle that the cosine inverse is going to return is between 0 and pi, and this is a positive ratio, so I know I'm in quadrant 1. I'm just going to go ahead and highlight that. So I have a quadrant 1 angle that this is going to return, where the cosine of that angle is 1/2, and that just requires us to draw out our special triangle to find our reference angle here. So I'm just drawing out my special triangle, 1, 2, root 3. The cosine of what angle becomes 1/2? Well, the cosine of pi over 3. So this tells me We have a reference angle of pi over 3 in quadrant 1, so therefore, maybe I should have written that down. We have a reference angle of pi over 3, and we are in quadrant 1, so therefore our actual angle is pi over 3. So these ones right here, again, when you're taking an inverse trig function of a completely different trig function of a special angle, just evaluate that trig function of the special angle. It's much easier. In fact, that's the only way you can kind of do these problems. Let's try this again. Right here, we have the inverse trig function of a completely different trig function, so sine inverse of a tangent. So the very first thing I'm going to do is figure out what is the tangent of negative 4 pi. And remember, tangent is actually pi periodic, so you could add a bunch of pi's to that and they would all be equivalent. Again, what I'm saying is the following. Tangent of negative 4 pi is the same thing as tangent of negative 4 pi plus pi, which is the same thing as the tangent of negative 4 pi plus 2 pi, and so on and so forth. So this tangent of negative 4 pi is the same thing as tangent of negative 4 pi plus 4 pi, or in other words, tangent of 0. But we know the tangent of 0 is 0. And this was in our previous video on evaluating inverse trigonometric functions. If you have the sine inverse of 0, that's a quadrantal angle. So I would prefer instead to figure out, okay, what would I plug into? Because remember, this is going to return an angle where the sine of that angle is equal to 0. So the question is, what would I plug into the sine curve to get an output of 0? And remember, the inverse trig function, the inverse sine, will only return an angle between negative pi over 2 and positive pi over 2. So if you draw out your sine curve, only draw it from a negative pi over 2 to a positive pi over 2. Negative pi over 2 to a positive pi over 2. And you will see at 0, it crosses the x-axis. That is, sine of 0 is 0. So therefore, the angle is going to be 0. Because again, sine of 0 is 0. Kind of a fast example. So let's try something slightly different. What about the secant inverse of the cosecant of 3 pi over 4? Okay, so this is going to take just a little bit of thought here. I'll write it this way. This is secant inverse of the cosecant of 3 pi over 4. Well, let's go ahead and worry about the cosecant of 3 pi over 4. 3 pi over 4 is a quadrant 2 angle, right? And the cosecant is positive in quadrant 2, so it's going to be positive cosecant of the reference angle. And cosecant of pi over 4 is root 2. So this is secant inverse of root 2. With me so far? I certainly hope so, because the cosecant of pi over 4 is the reciprocal of sine of pi over 4. And so sine of pi over 4 is 1 over root 2, so the cosecant should be root 2 over 1. Now, we're just going to ask, what is that angle that you would normally plug into the secant to get an output of root 2? So where the secant of that angle is root 2. Well, think about it. Secant is positive actually in 2 quadrants normally. It's positive in quadrants 1 and 4. However, the secant inverse will not return into quadrant 4. The secant inverse returns into quadrants 1 and 3. That's the weird thing about secant inverse. Well, of those 2 possibilities, where is the secant going to be positive? Quadrant 1. So now all I need to know is, from our special triangles, which in this case would be the pi over 4 right angle, pi over 4 right angle, we get 1 root 2. So we can easily see the secant of pi over 4, which is hypotenuse over adjacent. The secant of pi over 4 is going to give me that root 2. So my reference angle is pi over 4, and I'm in quadrant 1. So my actual angle must be pi over 4. All right, let's see if we can make it a little more challenging. And I went to the next example and realized it's no more challenging than this. So I'm going to go ahead and make up an example to make it a little more challenging. So let's suppose that you had instead a secant inverse of, let's do a tangent maybe. No, let's do a sine. Secant inverse of a sine of 11 pi over 6. So let's start by reducing this down. That's a secant inverse of sine of 11 pi over 6. Well, 11 pi over 6 is in quadrant 4, so this is going to be a negative sine of the reference angle. And sine of pi over 6 is 1/2, so that's going to be the secant inverse of a negative 1/2. And accidentally, but pretty comically, this is an interesting problem because I'll just say it this way. This is supposed to equal an angle where, this should stop us in our tracks in a moment, secant of that angle will equal to a negative 1/2. I will tell you right now that is not possible because the secant will never be a number between negative 1 and 1. Secant, remember, is, I'll say but, secant of theta is either always greater than or equal to 1, or secant of theta is always less than or equal to negative 1. In other words, there is no angle I could plug in the secant to get an output of a negative 1/2. So interesting problem, but there's no solution. So no solution, or does not exist, whichever you want. Does not exist is often used in computers. So we'll just do that. And that was an accidental one. So let me go ahead and try a different one here. Let me make one up that actually does work. How about the secant inverse of the cosecant of 11 pi over 6? Now I can do some work. All right. First of all, that'd be the secant inverse of cosecant is just like the sine. And we know that in quadrant 4, it'll be negative. So this would be the negative cosecant of a regular old pi over 6. We know the sine of pi over 6, because we just done it, is 1/2. So the cosecant is 2. So this is the secant inverse of a negative 2. Secant inverse of a negative 2. And that should return an angle. Now, this is a very interesting pre-cal problem. So that's going to return an angle where the secant of that angle should be, it's supposed to be the angle, sorry about that. There we go. Should be a negative 2. Now, a little note here, kind of critical, is that the secant inverse returns angles that are either in quadrant 1 or quadrant 3. Remember, secant inverse and cosecant inverse are the oddballs. They just return in weird quadrants. Specifically, they return angles between 0 and pi over 2, or pi and 3 pi over 2. I'm not really containing the edges on these, even though technically they both contain one edge on each of those intervals, but I'm not really super concerned about that. So let's see. You have either a quadrant 1 or a quadrant 2 possibility here. And I'm going to tell you right now, quadrant 1 can't work because the secant is not negative in quadrant 1. So it must be the quadrant 3. Did I say quadrant 2? I meant quadrant 3. So it must be the quadrant 3 angle. Well, let's go ahead and find out, now that we know the quadrant 3 angle, let's find the reference angle. And this is going to be a special triangle. So the reference angle, let's go ahead and draw out my 30, 60, 90, or my pi over 6, pi over 3 right angle. 1, 2, root 3. And the secant is hypotenuse over adjacent. Hypotenuse being 2, adjacent being 1, means that our reference angle is pi over 3. So we have that's supposed to be a 3, sorry about that. So we have a reference angle of pi over 3 in quadrant 3. That means our actual angle, theta, which is the secant inverse of all this stuff. So let me just write that down below. Secant inverse of the cosecant of 11 pi over 6 is going to be, again, an angle in quadrant 3 with a reference angle of pi over 3. That's 4 pi over 3. And by the way, no, you cannot say that it's negative 2 pi over 3, because that is not in the range of the secant inverse. Secant inverse does not return negative angles, so you can't do that. It's 4 pi over 3. All right. So that was the example I was trying to aim for, but kind of screwed it up on the first one. The final example in this video is just to rewrite a trigonometric function as an expression involving only x. This is a big skill as you move forward into calculus. Although it doesn't get used actually that often in calculus, it's still big enough that it's important you know how to do this. So here we go. We have the sine. Oops, let me use my black ink. Sorry about that. We have the sine of the tangent inverse of x. And we want to write this only with x's, no trig functions. Well, that's the same thing as the sine of theta. Notice I continually do that, where theta is equal to the tangent inverse of x, which implies the tangent of theta should equal x. Notice I'm always doing that. I'm replacing inverse trig functions with angles. Now, it is important here to note our angle, because it's returning from a tangent inverse, must be between a negative pi over 2 and a positive pi over 2. So let's see. We have no clue, actually. There's no restrictions on tan inverse right now, other than that it returns an angle between negative pi over 2 and pi over 2. So there are two possibilities. You have your angle in quadrant 1. And in that case, the tangent of that angle is x over 1, opposite over adjacent. And the hypotenuse right here is the square root of 1 plus x squared. The other case is that the angle that the tangent inverse is returning is in quadrant 4. Well, if that's the case, again, the tangent of that angle is still opposite over adjacent, and the hypotenuse is still square root of 1 plus x squared. In either case, what is the sine of that angle? In both cases, the sine is x over the square root of 1 plus x squared. Again, x over the square root of 1 plus x squared. So in both cases, the sine of the tangent inverse of x is x over the square root of 1 plus x squared. And so we now can rewrite the sine of the tangent inverse of x as just x over the square root of 1 plus x squared. If it's a well-formed problem, you should be able to always rewrite that trig function as a single statement like that. All right, this is the end of this video. And in the next video, you'll see applications of right triangle trig and the use of their inverses, or inverses in that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.